So I don't know if you agree with me, but I think this has been a really good conference so far. We learned new tricks. We learned how to design better software, how to make it more resilient. And now we are going to see what happens next. That is how to keep the system running. And usually that is done just by observing how the system behaves and making sure that nothing is missing from our outlook. So a very quick word about myself. I work at DataSift, where we ingest, process, augment, and filter about 10,000 messages per second. We get the Twitter fire hose in real time, and many other sources. If you are interested in knowing about what we do, that's a link there that explains our architecture. It's a bit old, but still relevant. In the past few years, I've been really lucky to be on several large-scale projects. From those projects and from the people I work with, I learned a lot about what it means to keep those complex systems up. And I certainly know and now understand the importance of monitoring and good reporting. So we live in an age where everything is big, everything is complex, and to handle the complexity, we have a lot of parts that form our overall platform. This means that any downtime can be really a big problem for the business. And if we start seeing problems, like we don't have any output from our system, then it's difficult to find out where the actual problem is in the architecture. There can be 1,000 things that can go wrong. So it's very important to understand that obviously observability is a critical feature. So you have to bake monitoring hooks into your application to collect all the metrics you can. And of course, collecting metrics is just one part of the overall problem, because if you don't look at them, they are pretty useless. And good reporting is usually really, really difficult. Especially when you have to handle millions of events per second, spotting the important ones is really hard. So what I came to realize is that the dashboards and the BI tools in the past 20, 30 years have not done a very good job at helping us at this task. They probably missed the point entirely focusing on all sorts of wrong problems. And they fail at communicating, which is the most important thing, the most important feature we want from a good dashboard and monitoring dashboard. So I think that monitoring dashboards are too important not to be left in the hands of pie chart lovers. So let's see a few things that we can do to make dashboards better. And I would do it by taking a step back and understanding who is going to use dashboards. And that's humans. It's not machines. Like Aral was saying in his keynote yesterday, we need to think about humans first. And to do so, we need to understand a little bit about how we think and how we make decisions. That's what we usually call cognitive science. This whole talk is heavily inspired by this book. I read it last year. It's about statistics, economics, and how we think and how we make decisions. And I thought that many of the things in these wonderful books apply to system monitoring as well. So this book is a tale of two systems. And those two systems are the modes that our brain operates on. There is one mode which is fast and apparently doesn't require an effort, like answering 2 + 2. We know it's 4. We don't need to think about the operation itself. And we can call this system 1 in many ways: intuition, instinct, gut feeling. And then we have a slower thinking mode. So that's something that requires a lot of attention, that is effortful, like computing the other operation. It's not impossible, but we need to recollect all the steps on how to solve it. Then we need to keep in mind all the intermediate results. And finally, we can, after a lot of effort, answer the question. And most of the times, we don't even care, so we don't bother. The reason why the distinction is very important is that we have only a finite capacity for the second. During the day, we can only allocate so much attention to tasks. So it's very, very important that we preserve the attention as much as we can for when we need it. And in normal mode, we should really rely on our intuition, our instinct as much as possible. Mind you, the system 2, the slow thinking, is always there to double check, to regulate what the intuition is coming up with. But is, as I said, is limited and can only be used so much. So the first system 1, fast thinking, is there primarily for one function. It's there to model our what we consider normality. It's there to codify the environment around us under normal conditions. Because once we know what is normal, then we can be surprised. We can be surprised by what is not normal, what can be a threat to our environment. And so that's when we switch on our attention and make it, our brain really do the hard work. Because that's when we really need to expend our energy. So how does this relate to monitoring dashboards? Well, in my view, monitoring dashboards should be there in the background, giving, after a very quick look, giving us a warm feeling that everything is normal. And then we have alerts that can trigger something else, that can create a surprise. So we can then switch on our attention and focus on the problem that was recognized by the system, and we can then spend energy in actually debugging the problem. This is a picture of all the monitoring wall. And as you can see, we also have a siren with connected to a Xenos alert. Whenever there is something wrong, it sounds. So it's a very effective way of attracting our attention. So there are many ways we can use to improve the way we attract our attention by not wasting our CPU cycles and only color the attention on important stuff. And color and over-imagery definitely make it harder to spot important information. So take this graph and take this one. Now it's immediate that this is what we should focus on. We only highlight things that are problematic. We shouldn't really care about analyzing what's on the board. The dashboard should tell us immediately. It should really call our ability to process information visually. The other mistake we often make is we add a lot of data onto our dashboards. And we often require to read long descriptions just to make sense of what's in the graph. This is a beautiful infographics created almost 150 years ago. And it represents the march of Napoleon's army onto Moscow. And I believe it's a masterpiece of information density. It shows the path of the army along town by town after town up to Moscow. It shows the size of the army as it reaches Moscow, and the black line is the size of the army that comes back home from Moscow. And you can also see here the temperature that happened to be at the time while the army was in each different city. Now, this is a great infographic, but I think this is a perfect example of what a dashboard should not be. Because I don't want to spend 15 minutes reading a graph, reading a legend, reading a description, just to make sense of the dashboard. That completely consumes my attention, and I can't do anything else afterwards. One thing the previous graph was good at is that it gave numbers a visual shape. If you take those numbers that are really important, and if you try to memorize a few of them, I bet you can't remember more than 2, 3, 4 if you have a really good short-term memory. But give it a visual shape, and our brain, our visual cortex, can take a snapshot of the graph and immediately memorize the whole shape, so we can hold 12, 14, 15 values at one time very effectively. Dashboards are not analysis tools. There are analytics dashboards, but monitoring dashboards are not analytics tools. So when we cram them with tons of data like this in this example, all I'm reminded of is something like this. And I'm overwhelmed by a sense of doom and despair, and I think I'm never going to be able to understand this stuff, and I'm going to die, and I don't want to die, I'm too young for that. So I think that we need to really understand we don't need data. We don't need to analyze things. Monitoring dashboards are there, only exist to answer one question, one simple question. Is everything all right? Is there any issue? No? Good, see you later. So that's all. The basic function of monitor graph is there to tell us everything is fine, or no, actually there is a problem. Because otherwise, a complex dashboard can create a lot of fatigue in our brain. So it depletes the finite capacity for attention that we might have, and we no longer have it when we really need it. So in order to preserve the attention, our brain plays all sorts of tricks on our mind. So take this question, for instance. It's a brain teaser, and it's not particularly difficult. But especially if we are tired, like now after 2 days of listening to people talking, all our brain is actually reading is 555, 100, 100. The answer must be 100. Now, of course, so what happens here is that the intuition is suggesting an answer which is not always correct. And of course, the system 2, our capacity for attention, can reject the answer that was given by system 1, by fast thinking. It can really spend some of the finite capacity and work out that the correct analysis, the correct answer is actually 5. But our attention is often lazy, so it often endorses a heuristic answer that our instinct comes up with. So what happens there? Whenever we are tired, our brain tends to swap out a difficult question, a difficult task, for an easier one. It applies a heuristic. That is an optimistic way, a cheaper way of getting a result. So whenever I see something like this, a dashboard full of graphs, and maybe covered in tiny little text, my brain can decide what to do. It can either spend some of the finite capacity or use it up to figure it out and actually understand what's going on. Or, if we are lazy, it can choose to swap out that difficult task for an easy one, like thinking whether I can give the guy who created this dashboard a book on usability. What about these dashboards instead? Why can't we create these kind of dashboards? It requires no attention whatsoever. We immediately see the green color there, big. That's what happens now. That's the history in the past hour. And then down below with decreasing sizes, we have the history. So we can also relate now to a few minutes ago or a few hours ago. This requires no attention. This is letting our intuition do all the work. It's so much more effective. And in order to make sense to us, information also needs to be organized appropriately. Again, we should think who the user is. It's a person. It's not a machine. So Again, instead of organizing dashboards and graphs in a dashboard by the means of production, instead of making the machine's life easier by grouping all the dashboards by the tool that was used to generate those graphs, we could make it our life easier. And instead, we could organize the information by context, by the service that actually makes sense to us as users of the platform or the system. So whenever there is a problem, our dashboard should alert us on which problem is under trouble. And then we have all the information there to analyze the actual problem. It could be bandwidth, it could be too many transactions, it could be locking. At that point, we don't need to look at 10 different graphs in 10 different locations. It's all there. We could even go as far as adding some ancillary information to the overview that I showed a couple of slides ago, because that's useful to our brain to remember what happened in conjunction with certain events. The other mistake we often make is we don't let the information speak for itself. We don't display the information in its simplest terms. So we need to have embellishments of all sorts to steal attention. I mean, this is a classic example. Isn't it beautiful? It's a speedometer. Reminds us of a cool car. And it has all sorts of things like a 3D effect, glass reflection. It has bouncing needles, so it looks real. So we think about stuff we can add to this thing just to make it better and better, and it looks even better, to the point we probably go a bit overboard. So these kind of skeuomorphic dashboards are a bit pointless because they steal attention from the data, from the information. This looks pretty, well, without the bacon maybe, looks pretty, but it doesn't tell us anything, not only until we go beyond the shiny things. Pie charts are pet peeve of mine. They are difficult to understand. Why? Because our brain can't really compare round shapes as easily as square shapes. So it's difficult for us to understand who is taking the most of that single resource. And especially if we apply other embellishments like a 3D shape, then we distort information, which is the worst thing we could do, because we distort the value of the data, and we sacrifice accuracy for just aesthetic appeal. This could be replaced by a bar chart. Takes up about the same space on screen, and it's actually easy to sort and compare the values. Anyway, back to our friend, our brain. As I mentioned, our mind plays all sorts of tricks to conserve attention. So let's learn one or two things about our brain. The first fact is our brain is a machine for jumping to conclusions. Even where there is very little evidence, then we fabricate stories. We fill the gaps, and we tend to create a full picture, even if we don't have all the elements to judge what's going on. Take this example. What do you read in first line? A, B, C. Second line, 12, 13, 14. And unless we really pay attention, we don't even see that a piece of information up there is at least ambiguous. Another example, if we read something like this and approach the bank, the society we live in kind of primes our brain into thinking about this woman who is a businesswoman, and she's going to the bank to make a deposit or to sign a contract for a mortgage. And not for 1 minute we think that maybe it could be another kind of bank. Maybe she's on a boat and she's approaching the bank of the river. So, as you can see, our brain is very good at making up things and creating context even when it's not complete. So so this is where our brain can really bite us. this is an example of something that happened in production to us a while ago. Each of those lines represents the throughput of a single server, and we have several nodes processing the same kind of information. At one point, we had the cliff, and the conclusion from this graph is we are losing data. We are screwed. This is all the information we have. We know what's happening, right? Now, luckily for us, this was not the only information we had. We could compare the information given by this graph with other graphs, like system load on the servers, the throughput at network level between different hosts. And there, everything was fine. So it happened that the statistics server rebooted, and when it came up again, it didn't bring up the network interface that was deemed to receive the events. So again, this is an example of a conclusion we make based on limited information that can be wrong. Luckily for us, this was a case where we were wrong. So without the ability of analyzing data under multiple perspectives, we can miss out. We can skip, we can lose the meaningful information that comes from analyzing data from different facets, different perspectives. And maybe there is only one of them, only one of those perspectives that actually makes sense. So an easy way of cross-referencing two different kinds of information, or at least two different views over the same data, is a cross-tab like this one. So you can analyze the graphs vertically by service, or horizontally by resource. By the way, in order to jump to conclusions, our brain sometimes doesn't need any evidence at all, not even a shred of it. All it takes is a little bias. So information we have based on previous experiences, based on emotions that are related to something. So take, for instance, programming languages. We might have a very high opinion of C++ code as fast, efficient, rock solid. And maybe Java can only remind us of null pointer exceptions, garbage collections, or what nightmare. So if we end up having a pipeline that is inside is formed by different components written in different languages, whenever the pipeline as a whole doesn't do its work, then we jump to the conclusion that it must be the inferior language, the component written in the inferior language. So we use our bias to decide what is reality. So we fail to look at evidence first. As I showed you, our brain is really good at creating associations. And I want to run an experiment with you. I'm going to show in the next slide a word. I want you to say this a word where one letter is missing, and I want you to say the entire word. Okay? You ready? Well, almost everyone said soap. And we almost failed to see that there are at least other 3 words, slap, snap, or swap, that could fill the gaps. So again, what happened here? Well, I played a trick on you. I showed a word, which is wash, before the experiment, that primed you into making a correlation with the other words that were possible. And our brain, given it's really good at creating this kind of associations, discarded all the other options that hadn't a strong link, like wash and soap. So we use the attention for pattern matching. How can we exploit this inner ability of our brain to help us at doing a better job when we monitor systems? Well, we should really use this capacity that we have. It's a natural capacity. So we should use conventions like the sentiment associated with the colors. Green, good. Red, bad. Or familiarity with certain shapes that remind us of very specific things. Or even sounds, they evoke emotions. So As an example of a shape that evokes an emotion, take this graph. Whenever we see our monitor dashboard filled with a very tall graph and very spiky kind of waves there, then we get scared, we panic, we think everything is on fire. And most of the times, we do so unnecessarily, because all we do is we simply forget to normalize the data. So if the data is quite flat, it's not very spiky, it can fill the screen, because the dashboard tools usually, by default, maximize the shape on the screen, on the available real estate. So this shape evokes a very different emotion from the previous one. These shapes tells us, okay, there is plenty of headroom, everything is fine. So in the previous case, we woke up our attention, we consumed some of the finite capacity for nothing. Now, we've seen tricks that our mind plays to conserve attention. So let's see some other examples on how we can rely on our intuition to constantly monitor what's happening in the background and actually conserve the attention for when we need it. On a more practical note, when talking about real-time monitoring, I'll just mention a few tools we can use to help us. Of course, it's important to have an arsenal of different tools, because we have things that are specialized for a certain domain. We have very good network monitoring tools. We have very good system load monitoring tools. We have application metrics we can use, or use business rules that we can measure. And let's not forget about unconventional ways of alerting us. They are really effective. Getting started with instrumentation is really easy. There are even EVMs you can download, and they are prepackaged. They come with all sorts of monitoring tools you can already use. They are ready to be used. At DataSift, we are quite happy with two of them in particular, which are StatsD and Graphite. StatsD is a daemon created at Etsy to send a lot of events in a non-blocking mode via UDP. So it's very cheap to throw a lot of those events. And Graphite is a library to collect those metrics and display them in a graphical way and then analyze the data. It's very, very easy to generate those events. And we can have different types of events. One is a simple counter or an absolute value, and the other one is timing information. So these two metric types alone cover most of our needs. To help us, we should also remember that it's good to structure the namespace to give a hierarchy to the metrics, the names of each metric. So it's easier to navigate them and retrieve them later. And this is an example of a Graphite output. So it's a graph. We can compare different values on the same screen. We can apply functions to each of them. We can create a difference, moving averages, differential, all sort of things. So it's really, really easy. Point and click, and off you go. You can stretch graph, compress it. It's really, really easy. I'm going to open a parenthesis on a common mistake we make when looking at real-time metrics. And this is all due to this shape. We are very familiar with this shape. It's a bell curve. It appears all over the place in every single possible thing you can imagine. The distribution of events is very often modeled after this curve. And what this means is that the majority of events is clustering around the center of the curve. And then we have two long tails before and after, where we have a lot less events that happen there. So we might make the mistake of ignoring the two sides and only focusing on the center. So all we do is we think about the average value, and that's all we see. a slightly better way of looking at this curve would be to analyze the standard deviation between the average and the current value. So if it fits the first area within one standard deviation of the mean, then that means that 30% of the values fits in this area. So if we are monitoring latency, for instance, it means 33% of all transactions are within that latency. 2 times the standard deviation is already over the majority. And finally, we have outliers outside 2 times the standard deviation. So that's where we should focus when creating alerts. However, in real life, this rarely happens. What the real distribution, in most cases, looks more like this. So we have a limited number of events, transactions, that happen really, really quickly. Usually because we have cached values, or because we have failure, and usually we fail fast. And then we have a very long tail of other events that happen more slowly. So what is quite obvious from this graph is that the average looks actually faster than most transactions. So this is where we should pay a little bit of attention. So average per se doesn't give you any idea about distribution. So my suggestion is almost to ignore it. Instead, monitor parameters like the 50th and the 90th percentile, maybe the 95th percentile, because they give a much better idea of the distribution. So for instance, the dark blue area means that 50% of your transactions happen before 20 milliseconds or whatever the value is, below that value. And we have a distribution of the other transactions that can go up to 200 milliseconds almost. So this is more representative of what happens for real. And given the 50th percentage is usually more stable than the average, it's also easier to set a threshold on it. So we can see that we can monitor spikes in the 50th percentage, and we can spot when things go bad. As I mentioned earlier, our brain is really good at detecting patterns. So let's have a look at a few shapes that we should recognize when we work with real-time systems and see whether we recognize them, make something with them. I already mentioned this sort of shape, and I didn't quite explain what happens in this case. What happens in this case is, first of all, if we are calm and relaxed, we start panicking because we see everything on fire. Then, once we are with our attention switched on, we might remember to have a look at the baseline. So we might have a look at a different part of the system to see what the expected value for this graph should be. And then we decide whether it was appropriate to panic or not. So instead, always remember to normalize the data and make the baseline obvious so we can see how much headroom we have. Even better, let the machine determine what baseline is or what the baseline should be. We do all sorts of things with machine learning today. It's not that difficult to analyze traffic, analyze latency, analyze different things, and create a model of what normality should be and alert when normality is no longer true. Of course, not all kinds of metrics can have a linear threshold. So your website might have visitors that come to your site at different times of the day. Maybe the traffic is highest in the morning or just after lunch, and then it goes down during the night. So what we would like to have is some kind of system that can create this snake-like shape around what's good. So we are still able to detect spikes that are not normal, but it's obvious that it's not easy to create those shapes because even if the pattern is more or less the same every day, it's not exactly the same every day. So there is a very little trick you can play with Graphite. You apply one single function to your data, it's the derivative, and that will effectively flatten your curve. And then it's much easier to set a band there that you can consider normality. And everything that is outside this band then can be triggered as an alert because it's an anomaly. As an example of the need to cross-reference different views over the same data, here it is. This is again the traffic on each node on our platform, node by node. What you might not have spotted is that one node at one point went away. Because this graph is very useful to give us an overview of the overall traffic. But it's not very good at telling us what's happening in each single node. So we can have a different view where we simply draw a line for each node, the traffic generated on each node, and we can immediately see when one of them is not overlapping the others as it should. Another pattern you might recognize if you've done some audio editing, it's this, when some values look like they are clipped. So you see like a flat area. And this usually happens when the resource you're trying to use is exhausted or saturated. Or it could mean that there is timeout. So after that point, your application is not responding anymore. So another shape you should learn to acquire as intuitive. And finally, we can see here another kind of traffic that is quite common as well. We might see spikes that happen more or less at the same time, day after day. And the first thing to do in this case is to look at your cron jobs. Okay, so one last example. I want to pull everything I said so far together. And I want to show you a great way of creating dashboards, modern dashboards that perfectly respond to the question we had before. So who is the target? Humans, not machines. And how we can make our life easier to understand what's going on without using up too much of our attention. We know heat maps. They are usually applied to geographical contexts, or we think about eye tracking software on a web page. But there are other types of heat maps, like these ones. I showed you one earlier, that are very, very effective. So color coding, the health of the system, minute after minute, hour after hour, is a great way of immediately seeing the state of the platform as a whole without requiring any attention. We can just glance at the graph, okay, all fine, I'll carry on with whatever I was doing. But we can also use a different kind of heat map. In this case, this is a picture of our old networking gear, so how the switches and the routers were connected. And we can use some tools to make those lines representing the traffic between any two nodes alive. So they constantly tell us the state of those links. Are they overloaded or not? This is a more recent picture of our network. We had to upgrade to 10 gigabit links and very, very fast switches. And again, this is quite helpful because the traffic is color coded and we see when there is a bottleneck between any two nodes. So this is nice and dandy, but it's not enough because it doesn't give us any context apart from bandwidth. So there is a nice tool called Cacti, which is actually a horrible tool, but can be used in a nice way to monitor data that is sort of network related. And there is a PHP plugin called the weather map that can be used in conjunction with Cacti to give shape, whatever shape we want, to the data that we want to display, the metrics we are collecting. And so we can do something like this. We can have a background image representing our architecture, our system, so all the services, and we can show, again, we can draw lines between nodes to show bandwidth, to show latency. So we can see whether a single augmentation service in that case is timing out, or we have a queue with a slow producer. And since it's color-coded, we can immediately spot where the problem is. No attention required. We let our visual cortex do all the work. And this can be used even for system load metrics, like CPU or memory load on a single node. Or we can check if we have slow DB queries, or if a disk is running out of space. So as you can see, this is an entirely new way of designing monitoring dashboards. And I hope you agree it's a much nicer way than what Cacti by default shows out with pointless graphs. To conclude, almost beer time. I am aware that everyone is tired, and I used up whatever was left of your attention. I just want to go over a quick summary of what we've seen. So, information density is, of course, important, but don't overdo it. So, keep the thing is, you should use colors when it's appropriate to do so, but not many. Only use colors to attract attention to things that require attention. Simplify things. We don't want to spend time analyzing things every time we look at the dashboard. It should be immediate, there, obvious. And then use tools that the machine provides, or use machine resources to calculate what's normality, to model normality, and to trigger alerts when those events deviate from the norm. And appeal to your intuition, conserve your attention. These are some references. Shameless plug, we're hiring if you're interested. Thank you very much for listening so far. Welcome. Are there any questions? Yep.
Sorry. Hi, your weather map, just a few slides back, you say cacti, yet in the footer it says graphite.
No, that's the PHP plugin. There is a PHP plugin that can also receive data from the Graphite API. So you can use cacti for network metrics, and you can get everything else from application metrics coming from the Graphite API. So you can use both. You can use the metrics coming from cacti or from Graphite.
All right.
It's very, very powerful. Yeah. That's a plugin that a colleague of mine wrote, by the way.
When you were using the derivative formulas in Graphite to flatten out like periodic graphs, you mentioned that you then alert when there's a deviation from that norm.
Yeah, of course.
What sort of thing do you use for that alerting?
At that point, you need to decide what your threshold is. So you need to decide what's normal, what can be considered normal. So every time you have something that deviates from the x-axis over a certain value, 20 milliseconds, or 50 transactions, under connections, whatever the value you're monitoring is, then you can decide that that is close to your headroom. So you might decide to alert based on the specific resource.
How would you actually alert, though? Do you have something monitoring Graphite that?
Well, you can either use Graphite to emit the information via the API, and you can then analyze the numbers. A perfect use case for this is, I don't know if you saw Ian's talk yesterday about complex event processing with React OS. It could be a feed into that kind of system, so you elaborate information that way. Or you pipe data into Xenos, where you can define all sorts of triggers, alerts that way. So you define your error condition, and then you let Xenos trigger if you are using Xenos or a similar tool. Yeah. Any other question? Yep.
At the beginning of the talk, you had a photo showing what you described as the old DataSift dashboards.
Yeah.
Is that right, the TV screens?
Yeah.
What are they like now? Do they retain any of the sort of things that we saw on that?
Yeah, they are pretty similar. We have just more of them. So we actually have, I think, 8 or 10 different monitors where we can, because the platform keeps growing, so we have more and more things to look after. So we want to have at least the most important metrics there every time for a quick glance. So we don't have to look at many different tabs on our browser to retrieve information. So they are pretty much the same. We also have specialized graphs like the weather map I just showed you for the network links. We have even information about the health of the system after deployments. Or we even have the deployment timeline there. So we can immediately correlate problems to certain events. So any information that can be immediate to process and can help us maybe doing the first step of the analysis. Anyone else? Yeah.
Yeah, I was wondering about the cascading failures and how so that you might have your one system causing alert and then it's just cascading, but you actually only care about the primary cause. Like, do you have any systems or techniques for dealing with that so you're just not overwhelmed by all those alerts when only one is actually important?
Well, yes and no. I think for a cascading error, the time component is important. So another thing we have on our monitoring graph is just a list of events that happen in the system. So a list of failures. So we can simply go in order what happened first and focus our attention on the first item first. Sometimes the events don't really arrive in the same order, but if it's not the first, it's the second. And at that point, our attention is switched on and we can figure it out. One last question? Or beer time? Yeah, I guess that's it. Thank you very much. Cheers.